Okay, we have another integral here today. This one's from MIT 2025, regular season number 7. We've got the integral from 0 to 2025, the fractional part of the square root of x dx. Okay, I'm gonna probably do 2 videos on this one, so there's different methods. Of course there's different methods. For this thing, for the fractional part, if you're not familiar with it, what we could do is if we have some decimal number like 2.31, the fractional part is just gonna return this, so it's gonna be 0.31. And in the case where you have an integer, like let's say we just had 2, this is gonna return 0. Now, the nice thing we can use for our integral, sometimes there's this definition: if you have the fractional part of x, you can break it up as x minus the floor function of x. Going back to this first example, the reason this works, if you plug in, so our x value is gonna be 2.31, so we would have 2.31. What the floor function does is it rounds us down to the next highest integer. So the floor would round this down to 2. You subtract this and you get this. So this is how it's going to work. So for this method, what I'm going to do, I'll keep this because this is going to be useful later, I think, if I'm remembering. I'm getting kind of confused, but for starters on this, what I'm going to do, the square root of x, let's just clean that up with a u substitution. So if I do u equal to square root of x, then square both sides, x equals u squared. Take a derivative on it. Dx is going to be just 2u du. So then when we substitute, the nice thing about 2025 is it's a perfect square. You plug it in there, you get 45. And 0, we plug 0 and we get 0. This thing's going to reduce to the fractional part of u now. That's nice. And then for dx, we're going to have 2u du. Let's bring the 2 in front, u du. But from here, we'll go right to this definition and write it that way. Just because this part is something we can integrate, the floor function is going to turn into an integer value. So just because it's going to be easy to deal with this way, so I can rewrite it as u minus floor function of u all times u. Distribute in the u, and let's see what happens. So the first integral is clearly going to be super easy, right? So that's going to be u squared. We just do that with power rule. Distribute this in here. We're going to have, well, I should have a du in there somewhere, right? So we should have, so let's do du minus 2, distributing in the 2 and the minus sign. This second integral is going to be just u floor function of u. Now for this integral, we can just do it, power rule, right? This is going to be u cubed over 3, evaluated from 0 to 45. And now in this integral, what we could do is split it up on integer bounds, and we can summarize it. So we can have like a general integral and then bring it into a sum. So how this is going to look is I'm going to summarize from n from 0 to 44 and create each of these integrals. So like we'll be going like n to n plus 1. Notice when the first one's going to line up, right, we're going to have a 0 there. For the last one, when n is 44, we're going from 44 to 45. Again, for any one of these, the floor function is going to round us down. If we just take a random integral in here, like 23 to 24, the floor, when the u values are between 23 and 24, the floor will round us down to 23, and we're still going to have this u here. So each of these is going to be an easy integral. So coming back here, with the floor, it's going to round us down to this lower bound, so we're going to have u times just n. So let's see what kind of simplification I can get. Here, the 0 is going to be nothing when we evaluate that. This one, maybe I'll leave it unsimplified for the moment. So we'll have this as 2/3 times 45 cubed. And then minus 2. Here, the n can come out front of the integral. But with the n out front, we can just go ahead and integrate. So again, we're going 0 to 44. N times integrating this is going to be u squared over 2 from 0 to 44. So let me just clean up the board and we'll see if we can finish this thing off. Okay, sorry, I had a mistake on the other board. This was supposed to be from n to n plus 1. Hope I can delete that so you guys don't see that in the video. But anyway, let's just go ahead and evaluate this thing. So what I can do, first of all, let's cancel 2 with 2 because you can distribute it in, factor it out. It doesn't matter. The constants are going to go away. So now here on this part, when we evaluate it, we still have the n in front. We're going to plug in n plus 1 squared, and then minus just n squared. But when we simplify this, this becomes n squared plus 2n plus 1. Then the n squareds are going to cancel out. Then let me actually start splitting this up. So I'm going to write this 2/3. I'm going to split out 45 times 45 squared, just so I can cancel this and get a 15 here. Then we're going to have this sum. Multiplying in the n times the 2n plus 1, we get 2n squared plus n. So now cleaning it up, 2 times 15 is going to be 30 times 45 squared. Then minus our sum. Now I can split it into two sums. So I'll bring the 2 out front. We'll have this one sum that's going to be n squared from n equals 0. But see, notice 0 is just 0. So I can start this at 1 without changing anything. And then our second sum, we're just going to minus, and this is just going to be an n from 1 to 44. At this point, you might see why I want two methods. It's because without a calculator, this is kind of a mess, this one. So when we do this number right here, 30 times 45 squared, I probably should have just multiplied it out earlier, like here. This is just 60, this is 60,750. So then here, we have the formula for the first 44 squares, which is going to be, so using that formula, it's going to be k times k plus 1, which is going to be 45, times 2n plus 1, which is going to be 89. This is all multiplied over 6. You see, I don't want to calculate that either. This one I can calculate. The formula for the first 44 natural numbers, it's going to be 44 times 45 over 2. Because I can cancel this with this and get 22. If I think about it like 2 times 11, 2 times 45 is 90 times 11. This part's 990. So let's see, if this is 990, what is this thing right here? Well, my paper says, because this would be a pain to reduce, so this number is 58,740. And so putting it all together, if you subtract from 60,750, 58,740 minus 990, you get the final solution of just 1020, and that's it. And actually, I should extend this because the 5870 does include this 2 here. So there you go, some gruesome calculations in the end. The other method I have will avoid this, but then there's some more algebra, so it's still a trade-off. It's kind of like, you know, if you have a calculator, it's not so bad. So, okay, that's it for today. Thanks everyone for watching. Have a good day.